Good morning, everyone. So I'm BI from Chongqing University, and it's really my pleasure to present our work. Our work is about pocket electronic nodes based on ultra compact sensor array chip. Basically, the most important thing for our work is we design an ultra compact sensor array chip, and I will introduce how we design the chip and fabricate the chip. So as we all know, there are many common types of sensors, such as the MOS sensors or many other sensors. But most of these sensors still face noticeable limitations, such as the size. They are also usually bulky in size, typically on the centimeter scale, and their limit of detection are often higher, and their response time are relatively slow. So I think the first task for us for developing electronic nodes is that we should develop high performance micro nano sensors with low limit of detection and faster response. So because we cannot get very high performance and very small size sensors, then the commercial in those products are already large, and they have a large device volume and cost, and the resolution and the sensitivity cannot meet the request. So to overcome these limitations, so our project aims to develop a handheld in-node microsystem that features small size, low cost, and simple operation while maintaining high sensitivity and reliability. So this is our design of sensor chip. Our chip is designed as a multi-layer structure consisting of sensor electrodes, a dielectric isolation layer, and a supporting silicon substrate. And in the right image, we can see the top view layout of the device. The entire chip measures about below 3 millimeter by 3 millimeter, and within this compact area there are 12 independent sensing areas. So this small rectangle is a sensing area, and each sensing area is about 50 micrometers by 50 micrometers, and these sizes are evenly distributed from the center to the periphery and are individually connected by the fan-out electrode traces. So after the design of our sensor chip, for fabrication, we integrated semiconducting single-wall carbon nanotubes and MEMS-based field effect transistor. So the high-purity SWSNTs were isolated from density-graded centrifugation and then deposited as a uniform monolayer using the LB technique, and this next the FET array was patterned by ultraviolet lithography. Basically, it is a typical MEMS process. So the top image is our 4-inch silicon wafer, and each square on the wafer corresponds to an individual chip, and this is the SEM image of our sensor chip, and you can see the small area. It is a sensing area. Because CNTs are so sensitive and so almost uniform in response to different gas. So to provide each sensor unit with distinct gas selectivity, we deposit 9 different metal oxides, like these 9 materials, onto the sensing resins. This was achieved using a custom designed shadow mask with 200 by 200 micrometer square opening, and we need to align precisely to the layout of the CNT sensor array. This material was these materials were deposited by electron beam deposition. So you can see the single chip and also 9 chip and also the mask, and we can deposit 9 different materials, and each color corresponds to one material. And this is SEM and the EDS mapping to show that the deposition quality and where continuous uniform titanium oxide film is confined precisely with the in-one sensing pixel. And after fabricating the sensor chip, we built a small system. It is mounted. The sensor chip is this is the sensor chip. The sensor chip is mounted on a 5 by 5 centimeter custom PCB, and this board integrates all necessary circuits for biosensing or other functions. And these are the function and the components we use. And a 3D printed gas chamber inspired by the human nasal turbinate is attached on the top of the to ensure uniform gas flow across the sensing array. Also, the power and the data are both supplied through the USB Type-C port of a smartphone, produce a fully self-contained and portable phone nose system, as shown in this photo. Regarding the power characterization, the sensor chip operates at 5 watts with a current of 0.44 amperes, and the consumption is about 0.22 watts. And also we have an integrated pump, a small pipe in this system. So the small pipe works at about 0.1 watts. So the whole power requirement of our system is about 0.32 watts for the entire system. Then after we fabricating, we making the system. So we use this system to solve a very challenging problem. It is to distinguish the NO and NO2. So this slide summarizes the sensing performance of our 9-pixel array toward NO and NO2. And so in this figure, in figure A, our sensors correspond positively to NO and concentration, and also they show different responses. And the 7th material has the highest performance with very low limit of detection. And so for the 9-pixel sensors, the NO and the NO2 they have a very similar. They have a very similar response. So this indicates that the individual pixel cannot clearly distinguish the two gases. So, however, the similarity matrix in figure C confirms that the overall pattern of the response across the array is sufficiently diverse of reliable gas discrimination using pattern recognition algorithm. So, so for distinguishing the NO and NO2, first we should build the database. So we have many tests, and this is our experimental concentration pairs with different NO and NO2 resources. Also, we created a broad calibration data set and applied a sliding window algorithm to expand the time series data, capturing the dynamic sensor responses. Also, we proposed a spatio-temporal networks and compiled a transformer to learn inter-sensor relationships with the temporal CNN to capture time-dependent patterns. So our our proposed network is so higher performance, higher determination coefficient, or other metrics compare CNN or SLTM. And figure A and B illustrate the prediction performance of our SNNet model for NO and NO2 concentrations, and the predicted values closely align with the reference line across the 1-to-1 ppm range, especially for the NO2. The prediction almost perfectly matched the true values, proving the most strong reliability. Also, we built a Android smartphone app, and we can operate it at this app. And this is a video show. This is a video show how we do the math, and we can see this is our portable pocket electron nodes, and others are the gas tube or MFC to control the flow of the NO and NO2. And we can see that this is the baseline, and if we input the gas, we can see the signal, and we can do the okay. Then we open the wall, I think, and we can see the signal, and we can do the prediction on directly on this software. So maybe so that's all for my presentation. Thank you very much, and I'll be happy to take any questions.